There we go. All right. If you want to, there you go. Sounds good. So let me see. Well, welcome everybody to the 1W-MINDS seminar. I am very happy today to have, everyone is very happy today to have James Murphy from the mathematics department at Tufts University as our speaker. He is an assistant professor of mathematics there, and with additional adjunct appointments in computer science and electrical engineering, and does a lot of interesting work on a broad range of problems in applied harmonic analysis, mathematics of data science, machine learning, high dimensional probability and statistics. And today, I believe, has a very interesting talk lined up for us about Wasserstein spaces and metrics. So I will give you the floor, James. Looking forward to your talk.
Okay, great. So can you see my slides okay?
They look good to me.
Okay. Hi, welcome everyone. Thanks for the invitation. Really happy to be here and to talk about some work that we've been doing for about 18 months here at Tufts. So the talk is titled Towards Intrinsically Low-Dimensional Models in Wasserstein Space, Geometry, Statistics, and Learning, which is kind of a mouthful. But the basic proposal that we're making here is to try to take some ideas that are very natural in linear spaces, things like principal component analysis, and more generally, thinking about a small number of generators being a way to parameterize sets for which you can do efficient statistical learning. We would like to do that in Wasserstein space. And so what we'll do is sort of lay out some of these ideas in the classical setting, discuss ways that they've been extended historically, then introduce some of the kind of necessary technical background on Wasserstein spaces, and then discuss some of the fundamentals of this problem, and at the end go into some work on actually how to learn generators in Wasserstein space. We'll try to show some applications as well. So let's see. So this work is joint with 3 PhD students at Tufts, Ruji Zhang, Marshall Muller, and Matt Wierenski. So Marshall and Matt did most of the work on the 2 papers that I'll be presenting on. And then this is also joined with 2 faculty collaborators at Tufts, Shuchen Aaron and Abby Tassisa. So the basic setting that I wanted to start with is just this observation that most of us are familiar with, which is that statistical learning and machine learning is hard in high dimensions, in the sense that if I have many observations for each of my data points or many variables associated to them, then, okay, if there's no additional structure imposed on the data, everything looks very far from everything else, right? That I can't use pairwise comparisons in this high dimensional setting to make any kind of inferences. So this is sometimes called the curse of dimensionality. There's many different formulations of this. The one that I think is most salient for me in the sense of thinking about distances is that if I take a uniform sample from a high dimensional cube, then the typical distance to a point's nearest neighbor is extremely large in high dimensions, right? So it scales something like number of samples to the -1 over the dimension. And so when capital D is large, this is very small. So rather, this quantity is very large, even for n large. So somehow everything is like floating in space. It's all just dust, and you can't make any kind of inferences. So this is certainly not something that has to doom all of our efforts. In fact, there are, I would say one of the main stories in machine learning, maybe from about 2000 to maybe 2010, was, a modeling approach that would try to let you get around this, right? And this sometimes goes under the name of like the manifold hypothesis, which says, okay, suppose that the data actually has a low dimensional structure in the sense that it lives near some low dimensional subspace or low dimensional manifold that is, let's say isometrically embedded in the high dimensional space. So what this really means is that I see high dimensional recordings for each of my data points, but there are some secret correlations, perhaps linear in the subspace model, perhaps nonlinear in the manifold model in general. But one might hope to devise methods that are going to depend on this intrinsic dimension in the crucial sense rather than the ambient dimension. So, probably people have seen this kind of picture before, but if what I've done here in this little visualization is take some points in R2. Each point is technically two-dimensional, but they all lie quite close to some low-dimensional circles, right? Just some one-dimensional manifolds, essentially. I've added a bit of noise. So it's approximately one-dimensional, right? So a large class of algorithms and sort of modeling approaches work from this as the hypothesis. The title of this slide, Think Globally, Fit Locally, is from a famous paper by Lawrence Saul and collaborators, where they propose a specific method to solve this problem of how to synthesize sort of locally linear, low-dimensional information into a global picture, a global set of algorithms for, say, clustering the data or performing supervised learning efficiently or finding low-dimensional visualizations associated to it. But a lot of methods in this area kind of work from this principle, not just the sort of algorithm they propose. And these go under the kind of general name of maybe manifold learning, where you try to take local pairwise distances that are going to be maybe meaningful because there's sort of an intrinsic low-dimensional structure, at least locally in the manifold case. So you make these low-dimensional inferences and then stitch them together, right? And somehow the stitching together is the difficult part, right? How do you do that? Is how many of these methods differ. But the basic picture is kind of roughly the same for these, which is that if I can use local Euclidean distances to find this low-dimensional structure, then I can compute geodesics, I can compute Laplacians or diffusions on graphs in this way. I can find low-dimensional embeddings and visualizations as well. Everything will work if I sort of tune the parameters right, assuming this local Euclidean information is meaningful. So what I want to do is problematize, as a start to this talk, the notion that the local Euclidean distances are meaningful, right? So I want to show just a very kind of synthetic toy example to illustrate that this basic assumption that the local distances are meaningful, that may not always hold. So the example I have here is kind of coming from like an image processing perspective, which is, imagine you have a data set which is 100-dimensional, so bad, but there is some intrinsically low-dimensional structure in the sense that these are images, okay? And each image is sparse, okay? So it's gonna be mostly black, 0 pixels, except there's one white pixel in each image. And I would like you to find a way of organizing this data for me. And okay, if I show you these pictures, there's clearly some kind of low-dimensional description of this data, right? It's the location of the support of this dot. But if I think of this as a high-dimensional vector and think about saying, okay, let's vectorize each of these images into 100 dimensions, then, well, what do the local Euclidean distances say, right? What is the distance to my nearest neighbor telling me here? It tells me nothing, because each pair of vectors is either distance 0 from each other, right, when they're the same, or their distance, say, square root of 2, right, if they are distinct, right? It doesn't matter if the pixel is spatially adjacent or very on the opposite side of the image. Everything is sort of equally far apart. If you think about these as high-dimensional vectors with the Euclidean distance, even nearest neighbors. So essentially, we need to change the paradigm yet again, right? We need to go a little bit past manifold learning here, or at least Euclidean manifold learning, if we want to find low-dimensional structures in these data. And I think that this is a nice motivation because it suggests that what we need to do in this case is pay attention to the support of these images. And making comparisons at the level of the support is helpful here. And in fact, very easy to compute, right? These are, in a sense, the spatial location of this pixel tells you everything about the distance between the support sets. But we can move to a more general setting and think about probability measures and how to measure distances between them in a meaningful way. So I'm going to make a jump to a sort of continuum mathematical formulation. So we'll consider the space of probability measures that are absolutely continuous and have finite second moment. So this just means it has a density and you have sufficient decay of the tails. And we're going to define something called the Wasserstein metric on this space of measures. And I'll just say I'm not going to be sort of maximally, I'm not going to talk about the largest possible sets in which these things can be defined. I'm going to sort of make a few assumptions that carry through most of the talk to make the formulations relatively digestible. But let us say we have two measures that have finite second moment and are absolutely continuous. And I'm going to define the Wasserstein 2 metric, which is a distance between them, as the square root of the following cost. So I'm going to minimize over a class of functions, T, or maps, I'll call them. And a map has an associated cost to it. So I take an input point X, and I take its difference with its output point, T of X, and I take the squared distance between those things. And then I average over all the probability mass associated to the input measure mu. So for each T, I have an associated cost. So this is going to be small when T stays close to X. Okay, so when I don't move the point very much. Okay, so not a very interesting problem without a constraint, right? And the constraint is that T has to push forward mu onto nu. So in a sense, T needs to be carrying the probability mass of mu to its sort of corresponding element with respect to the measure nu. So it's an optimization of over the space of functions, right? So I find hopefully the minimum T here, and that's going to somehow be meaningful for me. So let me show a visualization of what this function T sort of looks like. So this is from a great set of notes by Matt Thorpe that the reference is here. But the idea is that I have some measure, let's say mu on X, some measure mu on Y, and T will push forward mu onto nu if in some sense it's preserving the probability mass as I move from one space to another. This is a theorem, right, that in fact, under our assumptions, there will be a minimizing map T star, and we'll call that the optimal transport map. So what we think of is that is the map T, which pushes forward mu onto nu in the quote unquote most efficient way possible, where I measure efficiency as sort of moving the point as little as possible. Note that there are many ways that we could measure efficiency by changing this Euclidean distance squared to some other metric. And this is a sort of very well studied topic. But for us, we're going to stick with Euclidean distance squared. And I do want to say just a little bit about kind of the history of this problem, because it will come up later when we're doing computations, which is the formulation for optimal transport, which I just given is somehow like the old one, right? This is from, depending on how you date these things, maybe coming from pre-revolutionary France, right? From Monge in the 1780s. And it winds up being kind of not the right problem to look at in a lot of cases, that it may not have a solution in general. You may have non-uniqueness of the maps T. So an innovation in the 1930s and 40s came from Kantorovich, which was to notice that this problem, this optimization over maps that push forward mu to nu, can be relaxed by replacing that condition with the condition that we look at a sort of larger space of measures that have support on RD cross RD, and that these measures gamma, which are sometimes called couplings between mu and nu, should have marginals corresponding to the two input measures. So I'm changing the condition here. I'm integrating over this should be a double integral over RD cross RD rather than just RD, so my apologies. But I'm changing the problem by making the space of measures larger, but this winds up being an easier problem. This is, in fact, a linear program in infinite dimensions, and a sort of remarkable set of results show that, in fact, this problem coincides with the Monge problem, certainly in the case we are interested in, but in a relatively large class of measures. This will be something we double back to when we're talking about computing, but the maps, the Monge formulation, is important for the problem we're interested in. So the basic perspective that we have is that for a rich class of data, it is natural to model the observations, not necessarily as high dimensional vectors, but really as probability distributions. And we want to think about ways of developing low dimensional parameterizations in this space, right? So in analogy to something like subspace modeling or manifold modeling in Euclidean spaces, we want to think about notions of simple or intrinsically low dimensional sets in Wasserstein space. So going back to the subspace motivation, one way to interpret a linear subspace in finite dimensions is that there's a finite set of generators, and I look at all the things that I get from taking linear combinations of those. So in probability space, we have some constraints, right? Measures should integrate to 1. They should be non-negative. So I can think about, say, taking convex combinations of measures in a linear sense and create mixture models, okay? So this is one way to take combinations of measures. So very well studied in classical statistics. A way that is more compatible with the geometric structure of Wasserstein space, and I'll sort of explain what that means in a moment, is what is called Wasserstein barycenters. Right? So the idea here is I consider different ways of taking weighted averages of probability measures in the following sense. So I'll let delta P be the probability simplex on in P dimensions. These are going to essentially be my mixture weights for the barycenter. And I define for a fixed set of measures mu I and coordinates lambda, I define the Wasserstein barycenter associated to these mu i's and this lambda as the minimization of the following problem. So I define nu lambda to be the argmin over the space of nice measures of the average squared Wasserstein distance to each mu I. So I'm looking for a measure nu that kind of sits in between all of the mu i's. So this is sort of not so obvious, but it is in fact well-defined and unique under our assumptions. And I want to argue visually first that this is the right way of averaging in the space of measures. So let me just try to give a visualization. So what I have here on the top row are 4 different Gaussian measures. And on the bottom left, I'm showing you sort of the classical way to combine these measures, but by taking a linear mixture model. So essentially what this says is the coefficients lambda 1, lambda 2, and so on tell you how frequently to take samples from each mu I. So sampling from the measure on the left would say, okay, first sample from a multinomial with parameters lambda 1, lambda 2, and so on. And then, okay, that'll give you an index for one of your generating measures, and then go ahead and take an i.i.d sample from that. So in particular, there's no way to see new samples here, right? That sampling from the mixture just means you're sampling from one of the generators, right? There's not, in some sense, there's no novelty or generalization in the mixture model. The Wasserstein barycenter, on the other hand, finds a measure that sits between the other measures in this Wasserstein sense. So in fact, the resulting measure in the barycentric case is a new Gaussian, okay, that has sort of mean that's sitting between the means of the other Gaussians and has a covariance matrix that, it has a complicated relationship to the constituent covariance matrices, but it does in some sense sit between it. And I want to make it just sort of very roughly the case that Wasserstein barycenters are so geometrically satisfying in the sense that in this case, I have sort of 2 one-dimensional Gaussians. They're colored in dark blue and yellow, respectively. And what I'm showing you on the top is taking linear interpolations from the first Gaussian to the second, parameterized by a time variable t. And all it says is, okay, I'm going to define a new measure which puts 1 minus t weight on the first measure and t weight on the second, and I allow t to evolve. And what you're seeing is that as I go through the intermediate steps here, in the top, right, in the linear case, you're actually leaving the set of Gaussians and ending up with something that is bimodal. Okay, so all, in some sense, this geometric structure is being destroyed in this linear interpolation. On the other hand, on the second panel on the bottom, I'm showing you the Wasserstein geodesic between the 2 measures. And this is a bit more complicated, where essentially one takes the optimal transport map from the first measure to the second, takes an interpolation of that with the identity, and then pushes forward your base measure, mu, by that. And you see that, for one thing, it stays Gaussian. And in fact, the structure is preserved as I move along this Wasserstein geodesic. And I just want to comment that Wasserstein geodesics are, in fact, the barycenters between these Gaussians with the corresponding weights, 1 minus t and t. So in the sort of case of having just 2 objects, Wasserstein barycenters and geodesics are the same thing. And as soon as you have 3 or more, it's a little bit more subtle. So the problem that I think has been focused on mostly in this literature, albeit not entirely, is what we're going to call the synthesis problem for barycenters, which basically says, make me a barycenter. So if I give you some measures, mu1 through mu p, and some coordinates, lambda p, I'm going to ask you to solve this minimization problem. I'm going to ask you to find for me nu, which is the barycenter. So thinking about this in the linear case, right, this would be like saying, take the average of a bunch of vectors. Very easy to do in that case, because the corresponding variational problem there has a closed form solution. In general, there's not a closed form solution to this optimization. So very basic questions are open. Existence and uniqueness, statistical estimation procedures when you have only samples from the various measures, how to compute this efficiently in practice. So this is a pretty well-studied problem. And I'm just listing a very, very small subset of contributions, starting with McCann in the late 1980s and 1990s, and then sort of skipping ahead to work that was kind of kicked off in the early 2010s by Aguirre and Carlier, and sort of sparking some renewed interest in this. So visually, I think a good motif that I'm going to try to bring through the talk is to think about images as probability measures. So what I'm showing you on the right are MNIST digits. So the vertices of this little kind of triangle are MNIST digits from the MNIST data set, so a 3, an 8, and a 9. And then what I'm showing on the inside are various barycenters corresponding to particular choices of weight, right? So the one in the very, very middle has equal weights across all 3 of the generators. The ones on the edges are sparse, going from like 1/3 to 2/3 to 1. So the synthesis problem says, give me the vertices and then give me weights and fill in the pictures on the inside. So this is fairly well studied. So the approach that we want to advocate as one possible way of doing low dimensional or low parameter modeling in this Wasserstein space is to say, now fix the generators, right? Fix mu1 through mu p and allow lambda to vary, and think about all the barycenters that can be generated in this way. So we call this, this way of thinking, the barycentric coding model, in the sense that we are representing a particular probability measure mu naught, which lives in this space, through its coordinates lambda. So it's an association of a potentially complex probability measure to just a p-dimensional vector, which are its coefficient weights in this regard. So in some sense, this is like this quote unquote span of the reference measures, right? If we were doing kind of linear subspace modeling, this would be exactly saying, take generators and look at the ways you can combine them to get a new object. Here, we have some problems in the sense that there's not really a notion of there's not a notion of orthogonal projection. There's not like a straightforward connection between mu naught and lambda here. So that's the focus of one of our first, contributions, is to try to understand that connection. So to go back to that little motif around the MNIST digits, what we're going to call the analysis problem is, given mu naught and the reference measures, find for me the coefficients that represent mu naught in this sort of barycentric span. So this is analogous to, say, taking a subspace and projecting an object onto it. So if you're already on the subspace, give me some coordinate representations. If you're not on the subspace, find the best representative on the subspace. Okay, so this idea of analysis and synthesis is kind of trying to think like a little bit like a harmonic analyst, in the sense that you have generators, these mu i's, and I can either combine them to get a new thing that will be synthesis, or I can take a thing and try to represent it with respect to these generators and get some coordinates, and that's analysis. So that's what we're thinking about for the first part of this talk, is how to think about that problem. So this has been studied before, and I want to mention a sort of paper that was important for us by Boniel, Perret, and Couturi, where they formulate this problem, and you can think about different ways of running a kind of gradient descent scheme to find a good choice of lambda, if not optimal choices. But we were focused more on trying to understand, okay, very basic foundational questions for this model. So I'll get to those in a moment. I do want to contrast this with linear subspaces yet again, where there is a notion of, say, orthogonal projection that one can take advantage of to very efficiently find these coefficients. That does not exist here. So it's a little bit of a challenge in this regard. And I want to mention 2 other approaches that are sort of related to this, which is the geodesic PCA approach, which sort of several groups have worked on, including Bigot et al. And Casellas et al. And I want to mention a recent preprint from last summer in the archive, Tangential Wasserstein Projections by Gonzalez et al., that take a slightly different approach, but in some sense are motivated by the same core problem, which is to find low-dimensional parameterizations in Wasserstein space. So just some basic questions here. Suppose I have a measure that I know lies in this barycentric span. Is there a unique representation, right? Can I find a unique set of coordinates that generates it? This is, of course, not true in linear subspaces, right? That you typically have redundant representations. And is also not true in our case, albeit for kind of a different reason. So I wanted to show a picture here where I'm imagining I have 5 probability measures that are generating my barycentric span, and mu naught sits in that set. So one way you could have non-uniqueness is that mu naught, say, lies in the barycentric span of mu3, mu4, and mu5, and also on the geodesic between mu1 and mu2. So there would be a sort of 2 sparse coefficient solution corresponding to the representation on the blue curve, and a 3 sparse solution corresponding to the representation of mu3, mu4, and mu5. So generically, uniqueness is a subtle question, and certainly there are examples where it's not true. We'll talk about maybe ways to get more precise here and to correct for this later. So I guess one question that was sort of the jumping off point for us was, how can I check if a point is in the barycentric span, right? So how can I essentially determine if my projected distance is 0? So that'll be the first problem we address. And we'll say a little bit about the harder problem, which is, what is the kind of generalization of projection here, right? How do I find, in the case when mu naught, I know nothing about it in terms of whether it's in the span or not, how can I find its best representative in the barycentric span? So how can I say project an arbitrary measure mu naught onto the barycentric span? And we'll see that this third bullet point is a hard problem, but we can say some things about it in a few special cases. So the main theoretical result that came out of this inquiry in this regard is to characterize being in the barycentric span in terms of a closed form quadratic program. So the main theorem is that under some regularity conditions on the probability measures, essentially related to the densities of these measures and also the smoothness of the entropic map of the optimal transport maps between each measure and mu naught, under some conditions, then I can check if the measure mu naught is in the barycentric span by asking if the solution to a certain quadratic program is 0 or not. So I take the minimum over all lambda in this probability simplex of lambda transpose A lambda, and I want to see if that's equal to 0 or not. So the key point here is, what is A, right? What is this matrix? So this matrix is in terms of the optimal transport maps between the candidate measure mu naught and each of the mu i's. So I take those optimal transport maps and I look at how much they displace mass, right? So I take Ti minus the identity, and I take inner products across all of these different maps. So A is, in a precise sense, a Graham matrix, but in the tangent space at mu naught. And so I ask, okay, this is a positive semi-definite matrix. Does it have an eigenvector that with eigenvalue 0 that lives on the probability simplex? That's basically the question here. So let me say just a little bit about what's going on with this and where this matrix A comes from. And then we'll talk about computation. So the basic idea is to do a little bit of calculus in this Wasserstein space. So we think about this so-called variance functional. So I'm going to fix lambda and then look at the functional which I'm trying to minimize when I compute a Wasserstein barycenter. So for fixed lambda and fixed mu i's, G lambda has a minimizer nu at the Wasserstein barycenter, right? It's the point that on average is closest to all the reference measures with weights lambda I. So if I differentiate, so fixing lambda, if I differentiate this in the probability measure nu, I get a Fréchet derivative, which is of the form negative sum from I equals 1 to p lambda I times a function, right? Times the optimal transport map from nu to mu I minus the identity. And this is, a result that comes up a few different places in this sort of Wasserstein barycenter literature. So the point is that I'll be at a critical point if this is equal to 0 at every point of the support that I'm looking at. So I need to essentially, find out the choices of lambda, right? The coordinates lambda 1 through lambda p, so that the gradient of G lambda is equal to 0. Okay. So I end up with a problem that says, okay, when is this gradient equal to 0 for what choices, if any, of lambda? And that's sort of the key point, is that I can actually then write this gradient of lambda, of G lambda. I can look at its norm. I need that to be the 0 vector, but with a little bit of algebraic manipulation, I can actually write that in terms of my matrix A. By taking this sum in terms of this convex combination of the transport maps, I can take that and turn it into a quadratic form with respect to the matrix A. So the, I guess, point is that we sort of shift perspective from differentiating with respect to the measures and thinking about what it would mean to be a barycenter, to then saying, okay, is that condition satisfied for any choice of lambdas? And that becomes a program, an optimization program in lambda. So that presupposed that mu naught was in the space of barycentric coordinates, right? That we can find that specific set of coordinates, which does give me mu naught as a barycenter by solving that quadratic program. So otherwise, right, if there's no choice of lambda for which that's equal to 0, the theorem doesn't say too much, right? It doesn't say anything about whether these coordinates lambda are going to be meaningful in the case when mu naught is not in the barycentric span. So this is when we're getting back to this question of projection, right? So if I have just an arbitrary measure mu naught, which I don't know if it's in the span or not, maybe it isn't in fact, I can still write down this quadratic program, right? I can still write down the map lambda goes to lambda transpose A lambda, and I can try to minimize that over the symbol X. Does that mean anything, right? Is that a useful construction even when you're not in the barycentric span? So the right-hand side of this sort of equation here, the argmin over lambda of the sort of distance between mu naught and a barycenter, this is like projecting mu naught onto the barycentric span. So I'd like to get my hands on lambda. And I know that I have equality here in the case when mu naught is in the barycentric span. I have equality between the right-hand side and the solution to this quadratic program. Is there a sense in which these are close in general, right? Can I solve this quadratic program to get projected coordinates in general? The answer is no. In general, we don't have a relationship between these things, but in certain cases, actually, you do have equality, that I can solve this quadratic program in general to get the projection. So this does require some pretty restrictive assumptions. This requires the measures that I'm using, mu1 through mu(n), to be what are called compatible. So this is a statement about how the optimal transport maps relate to each other in the following sense. So let's let Tij star be the optimal transport map from a measure mu(i) to mu(j). So I'm going to say this whole collection of measures is compatible if I have the following, in some sense, like commutativity between the optimal transport maps. So we'll say it's compatible if the optimal transport map between mu(i) and mu(j) is the same as composing the optimal transport maps from mu(i) to mu(k), and then putting mu(k) to mu(j), right? That I can basically factor through the optimal transport maps to any one of the other measures. So this is in general not going to hold, right? Like in a sense, it's a measure zero condition on the space of measures, right? That if I take, n random measures and ask are they compatible, the answer is typically going to be no. But there are some special cases when it holds. It holds in general for one-dimensional measures, as long as they have continuous densities. So that shouldn't necessarily tell you very much, right? Optimal transport in one dimension is quite a bit simpler than in general. But it is nice case. It is true for some Gaussians, essentially, if they all have the same eigenvectors. And it's also true for radial transformations of a common measure. So if I have sort of one base measure and I apply sort of radial transformations to it, then that induced set of measures is going to be compatible in this sense. So if you're compatible in this sense, right? So if the measure that I'm trying to project, mu naught, and all the generators, if they are sort of mutually compatible in this sense, then I can solve this quadratic program to do the projection. So I can take a quick pause. I can answer any questions, take a quick pause, or I can continue.
There is one question in the chat, I think about several slides ago, about guarantees for structure preservation of the centers. I think it was like maybe the slide 5 or 6. And Zhu Feng, if you want to discuss, if you want to ask your question verbally, feel free to do so.
Yeah, thank you. Can you hear me?
Yeah, go ahead, please.
Yeah, I think my question goes up a few slides after. Yeah, here. I think the result to preserve the structure is amazing. I'm thinking if there are some theoretical guaranteeing for the preservation of structure.
Yeah, I mean, this is I guess a well-known theorem in this community that Gaussians have Gaussian barycenters. right? And I can certainly, I mean, I think this is for example, in a 2011 paper in SIAM analysis by Aguirre and Carly. I think it's just called Wasserstein Barycenters or something like that. And they prove a lot of the kind of nice results that got this sort of line of inquiry started. And in fact, there is a formula for the covariance matrix of this Gaussian in terms of the covariance matrix of the generating measures, albeit it's not a closed form, right? It's sort of essentially there's a fixed point relation between the generating measures and the covariance matrix of the Wasserstein barycenter. So in fact, it's not very practical, in the sense that finding solutions to this fixed point program is itself an area of research. But there's a nice approach by some MIT statisticians. I think Philippe Rigelet is sort of the senior author on those papers, where they develop different methods to solve that fixed point equation.
I see. Does it mean those structure preservation mostly holds for the Gaussian mixture model, or it holds for any other distributions as well?
In general, yeah, there is structure preservation in terms of like where the supports and so on live. But I think the Gaussian example is sort of particularly nice in that you stay in the class of Gaussians, right? This is typically true for parametric families, which are characterized by, let's say, a center and a spread of deviation. Something like a Laplace distribution also has this property that the barycenters of Laplaces stay Laplace.
I see. Makes sense. Thank you so much.
Great. Any other quick questions before James continues? All right, take it away.
Sure. So let me just say a little bit about computing, because we do want to run this on some real data. So everything so far has been a continuum formulation. So we've thought about probability measures and how to think about these maps between them, where the measures themselves are absolutely continuous. So, in practice, what I'm going to see are some random samples from these measures. So this is, again, sort of a well-studied area where how do we approximately solve this optimal transport problem when I get, let's say, i.i.d. samples from the measures I'm interested in. So the discrete Kantorovich problem solves this linear program, right? So what I'm just doing is taking the continuum Kantorovich problem and sort of discretizing it. So I'm going to do a minimization over the space of bistochastic matrices. So that's this matrix pi. And I'm going to try to find the bistochastic matrix which sort of moves points as efficiently as possible. So I'm imposing, instead of having just Euclidean distance between y minus x, I have specific points, right? So xj and yk here. So I want to minimize over pi this cost functional. So the good news, right, compared to something like a discrete Monge problem, is that this is a linear program. Okay, so it is something you can get your hands around. It may not have unique solutions, as is kind of typical for linear programs, but at the very least, you can try to run off-the-shelf solvers on this. But there are better things you can do. The bad news is that the better things you can do typically have worst-case performance that's supercubic, right? So typical bespoke algorithms will be something like n cubed times polylog factors. I do want to say that a pretty active area is trying to improve this, right, via various forms of approximation schemes. And I'm just listing a very small subset of some of the more recent approximation schemes here that are typically going to tolerate a little bit of error in various senses to get, say, quadratic complexity in the number of samples. The one that I would say seems to be the most popular and that has some secondary benefits as an approximation scheme is to solve what's called the so-called entropic optimal transport problem. So what this says is take the Kantorovich problem and replace the cost with that original cost plus a little entropic penalty on the bistochastic matrix. So this is going to say promote more diffuse solutions to the optimal transport problem. So it's sort of I guess a good piece of folklore is that typical solutions to the Kantorovich problem have a lot of sparsity to them, right? In the sense that if they coincide with the Monge problem, you end up with like one sparse rows of the Kantorovich solution matrix. once you impose entropic regularization, you have a diffuse coupling rather than a concentrated one. But this problem is strongly convex, and there's nice parallel schemes using sinkhorn iteration that can give you a quadratic sample complexity, but we can sort of use this parallelization to actually make it faster and more practical than other quadratic approximations. So let me say a little bit about how we actually solve this problem, right? So the setting here is we have our measure mu naught, and we have our generators mu1 through mu p. I have access to i.i.d samples from all of them. And I want to find the optimal coordinate for mu naught with respect to these generated measures. So I'm going to solve the entropic problem. So what I'm showing here is essentially doing a minimization over the so-called dual potentials of this strongly convex program. And I compute what's some in the literature very recently has been termed the entropic map, which is essentially a regularized version of the optimal transport map, which has a little bit of essentially it's taking this diffuse coupling coming from the entropic Kantorovich problem and then doing a conditional expectation over one of the variables to get an honest to goodness map between the two spaces that you're trying to move between. So I get these estimated entropic points, maps ti hat, and I'm going to use those to estimate this matrix A. So this matrix A hat here is an estimation in two ways. First, it doesn't solve the problem that our theory is totally geared for, because it's a discrete problem that's being solved with entropic optimal transport. Okay. The second point is that it's based on random samples. So there's a statistical error here, or a variance-based error, depending on how the sample behaves, but there's also a bias because we're solving the entropic problem rather than the true optimal transport problem. So our main result here is to say if I estimate the matrix A this way, this sort of estimated Graham matrix, and get the coordinates by solving the quadratic program with respect to A, I get something that is close to the true continuum coefficients. So if I solve, if I go through this algorithm, then I can get a pointwise error in the expected error between the ijth entry of the matrix A and this estimate. And essentially it scales, unfortunately, exponentially in the intrinsic dimension of the data. So there's a -1 over lowercase d hiding in the second term of the error bound. And that passes to the estimate on the coefficients themselves, right? So I can get an error estimate on the estimated coefficients that scales exponentially in the data dimension, which we think is not, we think that can be fixed, right? That we're working on that. But right now, the best result we have is an exponential error rate. So it does suffer from the curse of dimensionality. And as one might expect, it does depend on the smoothness of these optimal transport maps, which is really the heart of the matter, is how efficiently can you estimate the optimal transport maps with these entropic maps. So let me skip just to a couple of applications. So we tried this on some image processing data sets, right? So the model here was we took some MNIST digits and we corrupted them in various ways. So one corruption model was to add some Gaussian noise. Another corruption model was to remove the center part of the image. And we're thinking about trying to do image denoising and in-painting, respectively. So the approach that we took was take these corrupted images, right? So I have an image, like I say, one of these 4s, and I compare it to other corrupted 4 digits. And I can use, say, a linear estimator where I compute like my closest representatives in the space of corrupted 4s and average those as a way to estimate the number 4. And so that's what I get in the second column. Here are these sort of linear estimates of the digit, right? And what you see is kind of expected, right? Which is that there's a little bit of distortion in these MNIST digits, and just taking straight pointwise averages are going to lead to these kind of artifacts in the data. Now, we can solve the same problem where instead of just linearly combining these things, I solve the corresponding Wasserstein barycenter with respect to the corrupted 4s. And what I see there is a much sort of more geometrically satisfying recovery, albeit compared to the ground truth on the right, there is still a little bit of extra diffusion on these images that we think comes from the entropic regularization. And one other example that I'll come back to at the end of this talk is related to natural language processing, where I think about a document as a probability distribution in word space. And what I can do is try to classify a document based on how close it is in various notions of Wasserstein distance to a training set. So we're going to look at here this sort of very kind of relatively simple in this community News 10, or so rather News 20 data set. So it consists of 20 different topics, and each topic class has a sort of family of documents associated to it. So what we want to do is take a small number of training data from each of these classes and use those to predict new documents. And the approach we take here is we do everything in Wasserstein space. So we say, take a training little batch for each of these 20 classes, and then new document comes in. We can take its nearest neighbor in Wasserstein distance, and that's this blue curve. We can say if for each of the classes, find its sort of closest on average. So for my testing data point, I take its average distance in Wasserstein to each of my training classes, and I can use that to predict the label of the document. Or I can use my barycentric model in the sense that I can try to represent each document with respect to one of these classes and use the, let's say, one that has the lowest reconstruction error to label the class, or I can say take the one that has the sort of maximum barycentric coordinate when I group all the training documents together and use that coordinates label as my label. So what we see here is that the methods which use the barycentric mixing, right, the green and the red plots here, perform much better than the more naive use of the Wasserstein distances. So the way you can think of this is we're trying to project one of our testing documents into the space spanned by different document classes. And that is a more meaningful notion of representation than just computing nearest neighbors distances here. So actually trying to go through the work of projecting onto one of these spaces gives you, I guess 10% sort of improvement in accuracy in these problems. So let me wrap up with something maybe more related to signal processing and dictionary learning, which is everything we've done so far has sort of assumed we have a fixed set of reference measures. So we're either saying fix the generators and ask mathematical questions about how easy it is to project onto that space of generators, or in the numerical examples, we took random samples from our training classes and tried to do representations with respect to those. So the question now is, can I actually use observed measures, observed training data, to learn a good set of generators for this problem class, right? So the setting here would be, I show you a bunch of probability measures, and I want you to tell me a good set of generators for a barycentric coding model so that I can represent all my observations with respect to these barycentric combinations of these generators. Okay, so this is a very well-studied problem in classical signal processing. I would say the kind of cue for us would be like dictionary learning, right? I'm trying to learn good generators and good coefficients simultaneously. So this is sort of well-studied in Euclidean space, albeit doesn't always work very well. It is sort of a challenging problem in a lot of cases. It can be done in Wasserstein space as well. So let me just set this up and sort of discuss sort of maybe what I would say is the state of the art in this field, which would be to say, let's fix a dictionary, right? So these are like our generators, but we're going to be optimizing over it in these last few slides. So fix a dictionary DJ, J goes from 1 to M, and fix a coordinate lambda. Then we're going to call the object Bary, D lambda. This is just the barycenter associated to this dictionary D of reference measures and to the coordinate lambda. And I'm using slightly different notation here because we're going to have collections of lambdas, right? We're going to think about representing a family of measures. So we're going to use this bold lambda to denote one of the rows of this sort of coefficient matrix that's going to be coming out. So the idea to sort of think of Wasserstein generating as a dictionary learning problem came from Schmitz et al. In a 2018 paper in Cyan Imaging, where they proposed to solve essentially the following problem, where they would pick some loss function L, typically Wasserstein 2 distance squared, and they would say, okay, you give me training data mu1 through mu_n, and I want you to learn for me a dictionary D of measures and corresponding coefficients so that on average, my barycentric reconstruction with respect to the dictionary D is close to the observed data mu_i. So note that as soon as M equals n here, I can drive this loss to 0 just by taking the dictionary to be equal to the training data. So I'm typically imagining m is much smaller than n in this case. So I just want to remark that this is a very nice formulation, and there's a lot you can do with it, but it is ill-posed. And the easiest way to see this is to just imagine what you have are probability measures mu1 through mu_n that live on a Wasserstein geodesic between two measures, mu and nu. Okay, so this happens to coincide with the barycentric span of these two measures, right? Geodesics and barycenters between two measures are the same. So in this case, any two measures mu tilde and nu tilde, which extend the geodesic in a sense that I'm kind of being a little bit vague and visual about here, but in a sense that can be made precise. If I extend that geodesic, those two measures will also have the capacity to generate any of the training data. So I have an issue with being able to have sort of an infinite family of possible generators come out of this algorithm, right? So typically in signal processing, you would say, well, how can I deal with this ill-posedness? I might put some regularization on the problem here. So what's the right kind of regularization in Wasserstein space? So what we want to consider is what we call geometric regularization or proximity regularization. So we're going to define a regularizer RG, G for geometric, R for regularizer, that says, take your dictionary elements, DJ, and penalize me if DJ is far from UI, but I put a lot of mass on using DJ when representing MUI, right? So this regularizer is going to be large if MUIJ is large at the same time the distance between DJ and UI is large. So keeping RG small means representing locally, right? Representing MUI using the DJs that are somewhat close by to me, okay? So it's in some sense like taking, like trying to draw like the tightest possible, kind of quote unquote convex combination of these dictionary elements around your data, right? To be very careful about saying convex combinations here. It's quite subtle, but that's the picture you should have in your mind. So we add this regularizer. And what we propose to do is learn a dictionary by trying to find a dictionary and coefficients so that I reconstruct well by, say, having good barycentric reconstruction, subject to having this regularizer also being small. Let me just say a little tiny bit about this regularizer, which is, it does have a connection with sort of a notion of Wasserstein k-means, which would say, okay, suppose I have an additional constraint, right, which is that I am going to require my coefficients, which in principle, all I know is that they add up to 1 and are non-negative. They're just going to have to be 1 sparse. So essentially, I'm going to force the coefficient vectors to be combinatorial, right? So there's zeros everywhere except in one coordinate, they're 1. Okay, then we recover a sort of notion of like Wasserstein k-means, where I'm trying to learn a dictionary and an assignment matrix, a deterministic assignment matrix that assigns each observation to its closest DJ. So this is k-means in Wasserstein space. And in fact, if we fix a dictionary D star, what we see is our geometric regularizer is going to sort of be optimized to assign each point to its nearest dictionary element, right? So in a sense, if rho is going to infinity, this is like our problem is basically converging to like Wasserstein k-means. And in practice, what we're going to see is taking rho, the regularization parameter, bigger than 0, but like not too big, gives us sort of a nice balance between these things. So just very informally, we have a few recovery results we can prove, which is if I take the sort of soft version of this problem where I add the reconstruction and the regularizer and replace it with the kind of hard version, as you might kind of expect from sparse signal processing, and write it, say, I want to minimize the reconstruction, right? I want to have perfect reconstruction. And then within that constraint, I want to use the dictionary atoms that are closest to me. So if I try to solve this sort of constrained optimization that tries to minimize the geometric regularizer subject to perfect reconstruction, then for one thing, this resolves some of the non-uniqueness issues that we had when just thinking about representing a measure mu0 in a barycentric span. That adding this kind of constraint to use nearby things essentially fixes this problem. And what's interesting about this is, in fact, this imposes a kind of, if not sparsity on the coefficients, and certainly a kind of attenuation or shrinkage on them under certain generative models. So, these things are a little subtle to sort of describe precisely, but under sort of particular generative models for your training data, what you're going to end up with is coefficients that are relatively concentrated on a very small number of dictionary atoms in this case. And the other, I guess, kind of result I want to mention is that solving this geometrically regularized problem, the hard version, solves the issue of non-uniqueness of the dictionary learning problem for Wasserstein geodesic data, in the sense that if I know my training data live on a Wasserstein geodesic, and I solve the hard version of the problem, where I'm trying to learn two generators that are as close as possible to my training data, subject to the constraint that those generators give perfect reconstruction of all my training data, then provably those learned generators will be mu and nu here, right? So this geometric regularization prevents us from learning these extensions, right? Now, we do not have a result for more than two measures, right? That we really need to use the fact that these are Wasserstein geodesics rather than arbitrary barycentric combinations. We really make use of the geodesic structure in Wasserstein space here. Yeah, let me skip over this because I'm almost out of time. This is, we basically just run a gradient descent algorithm on the objective to get the dictionaries. We do entropic regularization as well to make things sort of tractable and work faster. There's, of course, some subtlety with initialization for dictionary learning. We run Wasserstein k-means and then take the outputs of those as the initialization to the dictionary, which works way better than taking like random initializations. So let me just compare this to a linear reconstruction model with the same regularizer. So if I try to reconstruct my data where I use like Euclidean distances of linear between the observation and a linear combination as my loss, regularized by the same kind of geometric penalty, but with Euclidean distances rather than Wasserstein distances, I get kind of weird results on MNIST, right? So what I have here are my training data are sort of synthetic barycentric combinations of true MNIST digits, and I want to recover the generators. And on the top, I'm showing you the reconstructions that I get from running this linear version of the dictionary learning algorithm, and they don't look very good, right? On the bottom, I'm showing you running our Wasserstein version of a sort of the same program, and they look much more, I think, geometrically satisfying. They look like digits, right? And as you go down in the rows, the regularization knob is being turned up. So at the sort of the early rows, you only care about reconstructing. The bottom rows care more about reconstructing with nearby elements, and they look quite a bit better, I think, when you pick the Wasserstein distance and also the kind of right choice of row here of regularization tunable parameter. It's kind of not too big, not too small. Okay, last slide. We can go back to these document classification results and compare taking random training data with learning a dictionary associated to each of my document classes, and then using those elements in the classifiers. And what we see, so the random training data are the dotted lines, the solid lines are the learned training data that learn without supervision, but the dictionaries associated to each of the training classes. And what we see is a quite large improvement in performance by going through the work of running the dictionary learning algorithm to get the training data for your sort of simple classifiers. And what we see is that in general, picking large regularization is pretty helpful for these labeling problems of documents. So I'll stop there. Just two problems we're thinking about are kind of notions of representational capacity here. What happens as I add more and more measures to these barycentric spanning sets? Are they kind of filling out the space of filling out Wasserstein space the way things would work in a linear space? The answer is generally no. I think this is kind of a subtle question. And then, computation is a major issue for everything we do. We can really only work on sort of relatively small data sets with entropic regularization and a big machine. So one thing we're thinking about is sort of linearizing these problems, a la the sort of paper from Wang et al. In 2000. 2013, which I know has been a fruitful approach for several in this community. So I'll stop there. The papers are here, and I want to thank the sponsors. And if anyone has any questions, shoot me an email and try our codes. So thanks very much.
Yeah, thanks a lot for an excellent talk.